Okay, so the next presentation is then by Pingping, and he will talk about, now we move to point cloud representation of radars, and he will talk about how to improve the point cloud representation.
Good afternoon, everyone. My name is Pingping Cai. I'm currently a PhD student from University of South Carolina. And today I'm going to share my paper called MilliPCD, Beyond Traditional Vision Indoor Point Cloud Generation via Handheld mmWave devices. We know that point cloud is one of the efficient data structure to represent 3D indoor environment. It can benefit many downstream applications, such as building information modeling, floor planning, simultaneous localization and mapping, as well as 3D object understanding and recognition. Usually, we can use LiDAR or RGB-D cameras to generate a 3D point cloud. However, both of them have their own shortcomings. For example, the RGB depth camera relies on good ambient lighting. It may not work on zero or poor visibilities. While LiDAR can work under poor lighting conditions, they are expensive and cumbersome. So our question is that, can we find an alternative solution to generate point clouds using sensors that are cheap and robust to challenging environments? The answer is yes. MilliPCD wireless sensors provide an alternative to the traditional vision sensors. It has several advantages. First, MilliPCD can penetrate small obstacles and work under poor or zero visibility. Secondly, mmWave transceivers are lightweighted and cheap will be ubiquitous in all 5G and beyond smart devices. Third, mmWave have the capability to measure the depth information using technique like frequency modeled continuous wave. So our idea is quite intuitive. Since mmWave is able to capture depth information from one viewpoint, then we can identify the general structure of the environment by measuring and combining depth information from multiple viewpoints. However, to implement this idea is still non-trivial. We are facing two main challenges. The first challenge is the noise. We know that millimeter transceiver is sensitive to a strong reflector behind a weak reflector. So it will generate a noise point that is non-existent inside the environment, increasing the difficulty of reconstruct a clear point cloud. Well, the second challenge is poor resolution. Due to the limited number of antennas and bandwidth, the resolution of mmWave image is extremely low, and the generated point cloud could be extremely sparse. So to solve those challenges, we design and implement MilliPCD, beyond the traditional vision point cloud generation system for handheld mmWave devices by integrating traditional signal processing with advanced deep learning algorithm to generate clear and denser point cloud. To solve the previous mentioned challenges, we have several intuitive solutions. For the noise, our idea is that we can design an algorithm to identify the potential noise point. Then the following algorithm can learn to overlook those noise points and reconstruct better results. For the poor resolution, we can use upsampling to generate a denser point cloud. So in summary, our MilliPCD works as following. We first collect mmWave signals using handheld devices from indoor environment. Then we feed those signals into a reflection point generator to generate a coarse point cloud. Then we use a noise-aware shape reconstructor to generate dense point cloud from coarse one. Of course, the hardware platform we designed is shown in the figure. It contains a smartphone with RGB and depth camera, as well as the mmWave transceiver. It can collect ground truth point cloud, pulse, as well as the reflect signal simultaneously. And we have collected data from two different buildings. For building A, we have more than 1,100 training patch and more than 165 test patch. For building B, we have collected 231 testing patch. Then we feed those collect signal into the reflection point generator. It combines the mmWave signal from multiple poles, identify the potential strong reflection points, and generate a coarse point cloud by back projection algorithm and geometric transition. Then we use the north-aware shape reconstruction. To use deep learning techniques to reconstruct high-quality point cloud from coarse point cloud. As we mentioned, we first use a score predictor to predict a confidence score, which encodes a confidence of whether each point is close to the ground truth. If it is close to the ground truth, then it means this point is a clear point and it's not noise. Then we use a feature extractor to extract global shape features, which encodes the 3D geometric structure of current environment. Finally, we use seed generator and point upsampling to generate a complete seed point and upsampling to the desired resolution. After we design our algorithm, we need to prove the effectiveness of the proposed system. So to do this, we conduct several experiments. The first is a quantitative experiment. Especially, we use several standard metrics to measure the quality of a generated point cloud with respect to the ground truth and compare our result with the previous. The second experiment is a qualitative result. That means that we visually check the generated point cloud and compare them with the previous one. Finally, we use ablation studies to analyze the major components of our design. Our qualitative results shows that we can achieve better results compared to the baselines. And we also show some qualitative results. We see that our method can generate point clouds similar to the ground truth. But another question is that, can we still obtain good results on those unseen environments? So to do this, we use testing samples from building B. Note that our algorithm is only trained on training samples from building A, so they are different buildings. We see that our method is robust to unseen data with only a small performance drop. We also test the effectiveness of the confidence score predictor. We see that for those points that's closer to the ground truth, it has a higher confidence score, where for those points that are far away from the ground truth, they have lower confidence score. So it means our method can predict the score accurately. We also test the ability to generate a different number of points, and we see that even with 1,224 points, we can still preserve the structure of the point clouds. It means that our method is robust to the PCD with different resolutions. We also test the robustness to different scanning time, and we show that we can achieve good results even with limited scanning time. So although we have made several contributions, it still has some limitations. For example, when we measure in the ground truth point cloud, the field of view of the RGB depth camera is different from the MilliPCD transceiver. So we cropped the collect PCD based on the field of view and pose of the MilliPCD transceiver. So as a result, the ground truth point cloud may be incomplete. The second limitation is imaging small indoor target. The MilliPCD relies on the reflections from those objects to identify its shape. The resolution of the MilliPCD transceiver is low, so the reflection signal from small objects could be buried easily under those large objects like building walls or floors. Finally, is extending our MilliPCD to outdoors. Outdoor scenario is more complex. Outdoor scenario contains complex reflectors with different size, orientation, and even with moving object, so which cannot be controlled and are difficult to distinguish from noise point. So in summary, we propose the MilliPCD, a system that leverages advanced capability of 5G mmWave devices and deep learning models to enable beyond traditional vision point cloud generation system. And the experimental results show that our system performs better than the existing method, both in quality and quantity. Thank you. Any questions?
Yeah, we can have time for one question. Yes?
Thanks. I have a question about if you need to walk around to generate the whole shape of the room.
Yeah, we need to walk around. We use the handheld devices to scanning.
So how to stage the point cloud from the multiple frames of radar?
Yeah, we use the I think in our slide we have already mentioned that actually we use a traditional signal processing algorithm to combine the signal from different pulses. And we process it using this one, backpropagation and the geometric transition. The geometric transition translates the local, collects the reflected signal into and combines it into a global one.
Oh, okay. Thanks.
Okay, thank you again for the presentation. And so the next paper, unfortunately, the authors were not able to attend here, so we have another remote